In section 6.2, we want to take a look at how we can use integrals to calculate volumes of three-dimensional things. Now, the general idea is this, in that you've got some three-dimensional object, and now I'm drawing on the computer screen here, which means I'm drawing it actually in a two-dimensional space, but I want to think of this as a 3D object. It's kind of like a football or an M&M or something, I don't know. And I want to calculate the volume of this in the following way. I pick an axis running, well, the axis doesn't have to be going through it, but you pick a direction. And you say, I'm now going to take planes perpendicular to that direction and slice this thing up with it. So when I slice it by, a plane here, let me try that again. When I slice it by a plane here, that's perpendicular to this axis there, the slice looks like it might be something like this, some sort of, maybe that's a circle, maybe it's an ellipse, maybe it's some other shape. But the idea is, as you move this plane back and forth, move it this way, move it that way, that you'll get these different slices on this object, slices of this object. Each one of those slices, I want to take this slice and look at it and say, what the heck does this slice look like? So if I take this thing and say, oh, maybe this looks kind of like that. I don't know what exactly the shape looks like, but that's some slice. What I want to do is I want to figure out what the area of the slice is, and then give that slice a little bit of thickness. So I'm going to take area times a little bit of thickness. Well, that little bit of thickness is going to be a d something in whatever direction. Let's say this is the x-axis. Then this little bit of thickness is dx. So a little area of thickness, maybe it's a dx, maybe it's a delta x, whatever you're thinking here. But you got that little bit of thickness times the area. That's going to be a little bit of volume. You then need to add up for every one of these slices. For this slice, you get a little bit of volume. For this slice, you get a little bit of volume. Every single one of them, all the way from the start to the end, you're going to add them all up. Now, the way the book presents this is they definitely use a delta x here, and they say, okay, you're going to cut this up into 10 pieces. Oh, no, 11 pieces. Oh, no, 12 pieces. You're going to cut up into n pieces, and you're going to take the limit as n goes to infinity. Each time, you're calculating area times delta x for more and more slices and taking the limit as n goes to infinity. That's exactly what an integral is. It's the limit of a sum of things, right? So the total volume is, we're going to say, is the integral from some starting point here, A, to some ending point, B, of this area. Now that area may be a function of x, right? Because that certainly the area of this slice is different than the area of that slice, because this one's smaller than that one. So that area times dx, area times thickness, is a little bit of volume, and you add up all those volumes from A to B to get the total volume. Now, in this class, in a Calc 2 class, we do these problems where each one of these slices, when you look at the slice, it'll look the same as every other slice. Maybe a different size, but generally the same shape. Maybe all the slices are squares. Maybe all the slices are triangles. Maybe all the slices are circles. But whatever they are, they're all the same. When you get to a Calc 3 class, we will do these things with slices actually maybe even looking different. But it's still the same idea that we're calculating this volume by slicing it up, taking the area of each slice, multiplying by a little bit of thickness, and then adding those all up. Okay. So let's do an example. What I have here is a solid. I want to show you how I describe this solid. There's several of these problems in the homework in the textbook. So I'm looking straight down on it here, and what I see is there's a region in the xy plane bounded by the sine curve. Here's the sine curve. It starts here, it comes up, it comes down, it goes like that. So that's the sine curve. So the top of this region is bounded by the sine curve. There's another curve called the cosine curve, which is coming this way. Starts up here, goes down like that, gets to the bottom, heads back up again. Okay. Notice at the bottom, just after 3 here, this is 3, the lowest point, so that would be at pi. Cosine of pi is -1, so that's as low as it gets. So the stuff in between there, the sine and the cosine curve cross at pi over 4, which is about 0.75, and then they cross at 5 pi over 4, which is somewhere up here just shy of 4. So I'm looking at x values between pi over 4 and 5 pi over 4, and my region is completely contained inside of that. Now, the way I'm going to describe this solid is to say that every slice perpendicular to the x-axis, so you got to picture these slices come straight out at you, right? Each slice is a square. So when I look at this from the side here, when I look at this from the end, you can see the different squares. You can see kind of a little yellow square here and a yellow-green square, and there's all these squares that when you figure out how far across the region is, go that far up as well. So down here in the xy plane, right? So looking down at the xy plane, I see over here it's really not very far across that region, and so I take that same distance and pull straight up, and you can see that, you know, this distance going across here pulled straight up to make that square. And since I do that for every single x value between this x value and that x value, I got all these slices, I end up with this solid. And I want to know the volume of this solid. Okay. So let's write some stuff down here. So I got a region in the plane. The region in the plane is bounded by the sine curve and the cosine curve, and I'm cutting it off here between pi over 4 and 5 pi over 4. Not 5 over 4, how about 5 pi over 4? So from here to there, for each value of x between pi over 4 and 5 pi over 4, I've got a little line segment there, and I'm going to extrude that line segment straight out at you. Now I can try to draw that, but of course it's hard to draw 3D on a 2D thing. So that's supposedly coming out at you, so you're sort of seeing it on the side. Right here, it's coming out at you, kind of a bigger square, right? Coming out at you. Little square down here. Every cross section, every slice looks like a square. Okay, so the question is, what is the area of each slice? So when I look at each slice and say each slice is a square, the side length is determined by the distance from the top to the bottom. Well, the top is y equals sine x. The bottom here is y equals cosine x. So the distance across is the difference between them. So this distance right there is sine x minus cosine x. Of course, that would make this the same because it's a square, sine x minus cosine x. And the area here, the area of this thing as a function of x, is sine x minus cosine x squared. Each one of those areas, I want to give it a little bit of thickness. So each one of these squares, I give it a little bit of thickness to make a little kind of squashed cube. Okay? And then you add up all those bits of volume. So I'm going to say the total volume is the integral from pi over 4 to 5 pi over 4. Those are where I have slices. I'm not worried about stuff over here. I'm not worried about stuff over there. Only between pi over 4 and 5 pi over 4. So for those values, I take this area function, sine x minus cosine x squared times dx. Okay. Be careful with your algebra. Some people want to square this out and say sine squared x minus cosine squared x, and they forget to FOIL, because that's what you really got to do on this thing. I would suggest at this stage, I mean, you could FOIL this out and do the integral by hand. It's not too hard to do. But I would just type it into my calculator. In fact, I'm going to do that right now. And this, actually my calculator tells me that it's equal to 3.141592665, which makes me think it's equal to pi, which makes me think maybe I should have tried that by hand. In fact, I'm going to do it by hand just because here. Let's do a quick calculation by hand here. So if I square that out, I've got sine squared x minus 2 sine x cosine x plus cosine squared x. I'm integrating this thing from pi over 4 to 5 pi over 4 dx. Sine squared x plus cosine squared x is 1, so this is the integral from pi over 4 to 5 pi over 4 of 1 minus 2 sine x cosine x. And the 2 sine x cosine x is actually the sine of 2x. And I write it like that just because I find that easier to integrate. So that was equal to this, which is equal to this, which is equal to, integrate this now. The 1 integrates to an x. The negative sign of 2x integrates to plus 1/2 the cosine of 2x. And all of this is evaluated between pi over 4 and 5 pi over 4. So plugging in, I've got 5 pi over 4 plus 1/2 cosine of 10 pi over 4 minus pi over 4 plus 1/2 cosine of 2 pi over 4. 10 pi over 4, there's 1, 2, 3, 4, I'm counting pi over 4s. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's the same as pi over 2. Cosine of pi over 2 is 0. So this is just a 0. Likewise here, this is a pi over 2. So cosine of pi over 2 is 0. And I end up with 5 pi over 4 minus pi over 4, which is equal to 4 pi over 4, which is just pi. So yeah, the answer is just pi. Okay, but what did we do? Quick summary here. We calculate the volume of this thing by slicing it. We look at slices. We look at slices of this thing, which are all squares. We can calculate the length of the square by being able to figure out for each value of x how far across the region it is. So from the top to the bottom, from sine x to cosine x. So I just subtracted the 2. I made that the same as the side length going up. So the side length going across is the same as the side length going up and down. This one is the same as that one. So the area is that side length squared. The area is that side length squared. Where do I have that? There's that side length squared. And I integrate that thing times dx. So that area times a little bit of thickness in the x direction is a little bit of volume, and I add up all those volumes for x values between pi over 4 and 5 pi over 4. And in this case, it turns out to be pi. Okay. So there's several questions like that in your homework. Sometimes the cross sections are squares, sometimes they're circles, sometimes they're triangles. In each case, you just got to figure out what's the distance across your region. My computer is running out of battery here. Find the distance across the region and then use that in whatever way they tell you. Make a square out of it, make a triangle out of it, whatever. And give it a little bit of thickness, dx, and integrate. Anyway, we'll look at some other types that come out of 6.2 in the next video.